Okay, folks, we've got 85 participants in so far. There'll probably be a few more joining us as time moves on. So welcome to our first virtual meeting for the Ottawa Centre RASC, and welcome to members and visitors here this evening. I'm going to be the meeting chair, and Chris Tarrant's going to be moving the slides for me. So you'll be hearing a lot of next tonight as we try to synchronize things. This is our first time doing a meeting of this size, so please hang with us. We do have a question and answer box at the bottom of the screen. So we're going to move then to the next screen. I've got an important thing for you to look at here. Okay. You've probably heard lots of things about Zoom and some of the security issues around it. We're fairly secure because we're running in webinar mode. We're not in meeting mode. So we're not going to have anybody come in and bomb us with inappropriate audio or pictures. However, some people may try to hack into the meeting, and they may try to put a web link into the chat box or into the question and answer box. Do not click on any web links that might appear in the chat or the question and answer box. They could take you to a malware site. So just keep that in mind as we move through the meeting. We are not going to be checking the chat box this evening. That's for you to chat among yourselves if you like. If you have questions for the presenters, please feel free to use the question and answer box. I will read the questions out as we move forward. So let's move on to the next screen. So here's tonight's program. We're almost through the introduction. I've got a 10-minute astronomy news. I've got the Ottawa skies for April. It will apply to Sudbury as well. Rob Dick will be doing light at the end of the tunnel, but LED lights. We are going to take a 5-minute bio break in the middle of the meeting, and we have a bit of a visual challenge for you over the break. Jeremy is going to come in after the break for a year of aurora chasing. We're going to have observations and then announcements. So we have 3 new members, David, Aaron, and Jackson Mackey. Welcome. And we have 15 new members so far in 2020 in the Ottawa Centre. Welcome, folks. Okay, 10-minute astronomy news. So we can go to the next slide, please, and I will take us through this. On January 1st, 2019, the New Horizons spacecraft zoomed within just 3,540 kilometers of Arrokoth, a 36-kilometer wide object in the Kuiper Belt, the ring of frigid bodies beyond Neptune's orbit. It was the most distant planetary flyby in the history of spaceflight. Arrokoth lies 6.6 billion kilometers from Earth, about 1.6 billion kilometers farther away than Pluto, which New Horizons cruised past in July 2015. Since the flyby of Arrokoth, New Horizons has been beaming back information from its flyby and will continue to do so for at least another year and 1/2. The snowman's shape indicates that Arrokoth formed via a merger of 2 separate objects, and that this coalescence happened a very long time ago, back when impact speeds in the outer solar system were quite low. Collisions in the modern Kuiper Belt are too violent to produce an object with lobes as distinct and as undamaged as Arrokoth's, New Horizons team members said. So Arrokoth is a primordial body, a planet building block, or a planetesimal left over from the solar system's very early days. And each of its 2 lobes apparently came together in the same swirling, gravitational, collapsing cloud of dust and gas in the Kuiper Belt, far from the newborn sun, the researchers wrote in May 2019. That initial interpretation has stood the test of time, as it turns out. The mission team published 3 new Arrokoth papers online on February 13th this year, and reporting analysis of 10 times more flyby data than was at hand during the writing of last year's study. It takes a while for New Horizons to beam big data sets home. The new studies largely confirm and extend the original conclusions about Arrokoth, and they nail down the distant object's origin story. Arrokoth has told us how planetesimals form, and therefore made a major advance in our understanding of planet formation, said New Horizons principal investigator Alan Stern, a co-author of all 3 studies. It is very decisive. Arrokoth's cloud collapse birth was far from a given. There's a prominent competing theory about planetesimal formation called hierarchical accretion, which posits that the planetary building blocks are built up over time by high-speed collisions of objects from various locales. Hierarchical accretion is actually the more venerable idea, dating back 70 years or so, Stern said, whereas cloud collapse, also known as pebble accretion, was devised just at the beginning of this century. There's been considerable debate between the advocates of the two theories over the past 2 decades. But the 3 new papers show convincingly how Arrokoth was born, said Stern, who's based at the Southwest Research Institute in Boulder, Colorado. With Arrokoth, there are half a dozen lines of evidence that all point to cloud collapse, and you can't explain them with this hierarchical creation. Perhaps the strongest such evidence is provided by the object's shape. The relatively intact nature of the 2 lobes implies a very gentle collision, not a high-speed wreck. In one of the new papers, researchers led by William McKinnon of Washington University in St. Louis performed detailed modeling of that long-ago merger. Okay, hang on just a second here. Okay, sorry about that. I just got a phone call in. These simulations indicated that the 2 lobes likely formed from the same cloud of material, became co-orbiting binary objects, and finally came together in a slow and non-destructive fashion. Indeed, the models peg the collision's maximum speed at around 15 kilometers per hour, and may have been considerably less than that. This scenario is further bolstered by the geometric alignment of Arrokoth's 2 lobes, which strongly suggests that the duo orbited the same center of mass when they are separate free-flying objects, the scientists wrote. The new results may end a long-standing debate. Uniform color and composition of Arrokoth's surface shows the Kuiper belt object formed from a small uniform cloud of material in the solar nebula, rather than a mishmash of matter from more separated parts of the nebula. The former supports the idea that Arrokoth formed in the local collapse of cloud in the solar nebula. Another of the new studies, led by Southwest Research Institute's John Spencer, digs into the geology and geophysics of Arrokoth, which also points to a cloud collapse origin. For example, the density of craters on Arrokoth indicate the object is ancient, with a surface of at least 4 billion years old. And like McKinnon and his team, Spencer found a close alignment of the 2 lobes, whose poles and equators are geometrically in sync. They also determined, among other interesting finds, that the lobes aren't quite as flattened as they originally believed. In the 3rd paper, Will Grundy of Lowell Observatory at Northern Arizona University and his colleagues investigated Arrokoth's composition. They found the object is cold and extremely red, with methanol, ice, and carbon-containing organic materials on most of its surface. These complex organics are probably responsible for the object's red hue, the researchers wrote. The overall picture is also consistent with the cloud collapse birth, mission team members said. For instance, the compositional similarity of the 2 lobes suggests they formed from the same starter material. And I will leave it there. So we're going to take a look at the Ottawa skies for April. And this will apply to our folks in Sudbury as well for the most part. And maybe we'll move on to the next slide. Okay, so here are the moon phases for the month of April. Full supermoon is on April 8th. The full moon is known by early Native American tribes as the full pink moon because it marked the appearance of the moss pink or wild ground phlox, which is one of the first spring flowers. The moon has also been known as the sprouting grass moon, the growing moon, and the egg moon. Many coastal tribes call it the full fish moon because this is the time the shad swam upstream to spawn. This is also the 3rd of 4 supermoons for 2020. Moving to the next slide. Okay, so we have 2 comets that we've got up there right now that we're following. So we got Comet Pan-STARRS, and it will be visible in the evening skies. Its perihelion is on May 8th, at which point it should be magnitude 8. And then this is a new comet on the next slide, please. We have Comet C 2019Y4 Atlas. I thought this sort of was a cool picture that I got showing where it is in the sky. It's a bit of an eye chart if you're looking at your computer at home, but we're roughly in the middle top of where it is right now. This shows where it is with respect to the constellations. Next slide. This shows where the two comets are, roughly one above the other. Next slide. We had the Lyrids meteor shower this month. It's producing 20 meteors per hour at its peak, and it was discovered in 1861. The shower runs annually from April 16th to the 25th, peaks the night of the 22nd, 23rd. The nearly new moon will ensure dark skies for what should be a good show this year. Best view will be from a dark location after midnight. Meteors will radiate from the constellation Lyra, but can appear anywhere in the sky. Next one. We also have tonight, this is what Sudbury will see tonight. There's going to be a conjunction of Venus and Pleiades at, I think it's about 9:30, thereabouts, or roughly, yeah, in about an hour from now. This is what Ottawa will see. Okay, sorry about that. Okay, next slide. And this is what the conjunction will look like tomorrow. Ottawa is supposed to have clearer skies tomorrow. I think Sudbury tonight is between 20 and 40% clouds, so they might be able to see it. Okay, next slide. Okay, sunrise, sunset times. You can see that the days are certainly getting longer. Next slide. Mercury is not visible this month. There's no elongations going on. Venus is visible in the early evening. Mars is visible before sunrise. So the rise and set times are for the first of the month and the last of the month. That's how these are being displayed here. Next one. Jupiter is visible before sunrise. Saturn is also visible before sunrise. Uranus is visible the first part of the evening, and Neptune is visible later in the month before sunrise. And here's my cartoon of the month. Hopefully you enjoy that one. Certainly appropriate for what's going on right now.
Okay, starting with the first slide. One question I can ask you is light pollution a problem for you? Well, in 2012, you probably thought that, yes, it is, but I'm a bit busy and I can still see stuff from my home. And if I can get to a really dark sky, if I wanted to drive to FLO, that's our center observatory, and you can see the little dot on to the west of Ottawa. And indeed, maybe you did, and perhaps you continue to do so. But light pollution doesn't go somewhere. It goes everywhere. And the next slide shows you what's happened in the last 7 years. While you've been accepting the views from your home or tolerating your drive to Flow, Lennox Addington, or North Frontenac, this is what's happened. Flow is now entering the zone of significant light pollution. So if we go to the next slide, you can see that indeed, and to copy a bit of a song, oh where has night gone? It's been a long time passing. Oh where has the night gone? 'Twas here not so long ago. So the next frame, I'm going to be talking about light at the end of the tunnel. And of course, light can be interpreted in at least two different ways. Light can be, well, light, and it can also represent hope. So the next slide is when we begin to start our talk from a rather strange perspective. There's good reason to lament the loss of night. It's not just part of our psyche, it's part of our DNA. As hunter-gatherers, we depended on our photopic vision during the day to hunt, and our scotopic vision at night to survive the night, much like the animals we hunted and now study today. However, our society and our culture has progressed and now dominates the natural world. To see how it used to be, we need to travel far from home, like Chris Tarrant did, and we heard of his trip last month at last month's meeting. Artificial light has changed the cityscape. which has evolved in a haphazard manner for about 1,000 years. It's now a completely engineered environment. Well, perhaps not engineered in a positive sense, but certainly it is artificial. Most cities have a dog's breakfast of outdoor lighting. There's been little effective official control over what lights anyone could install. Even the city's approved fixture list is heavily populated with ornamental lights that have been proposed by property developers. And there's little enforcement of what light policies there are. Officials don't even understand what light is, at least most of them. For example, in Saskatchewan, they decided that light is not a pollutant because they claimed it wasn't a particle. Well, lawyers who craft the legislation and politicians who vote on it don't seem to know much about science. All this has led to an evolving urban landscape based on conflicting goals and misinformation. We don't need much light at night. We just want lots of it. And in our society, what you want, you get. But what we forget is that we must eventually pay the piper. And we're now just learning how expensive that can be. Next frame. Light isn't a luxury, though. It has a purpose critical to our perceived safety and security. Humans are diurnal species. We need additional light at night to extend our activity throughout twilight. We need it to illuminate hazards or for safety. It's needed for surveillance and security. It's needed to highlight urban features for navigation, and we want it to support an urban aesthetic to beautify the engineered landscape. Researchers and engineers have worked very hard to make artificial light as efficient as possible to save energy, but this isn't what's happening. Our society is increasing outdoor lighting by over 2% per year, while expanding the illuminated area by another 2%. Instead of saving energy, we're squandering the benefits of these technical achievements. So what's going on? Next slide. Think about this. 200,000 years ago, we learned to control fire. In the 1800s, we developed the incandescent lamp, which uses electric current to heat a metal filament into incandescence. But these are thermal light sources. Heat excited atoms to glow. At the temperatures available, 600 centigrade for fire and 2500 for a tungsten filament, most of the heat was radiated in the infrared part of the spectrum. Fire radiates primarily heat. Only about 0.1% is light, whereas the incandescent lamps have been engineered to emit about 10% of their energy as light. Next slide. Then in the 1950s, technology leaped forward with high-intensity discharge lamps, mercury vapor, then high-pressure sodium and metal halide, that have now peaked out at 10 times the efficacy of incandescent lamps. That's how much light per watt. However, at each stage of improvement, when light became more efficient, more light was used, negating the increased efficiencies. We can use more, so we do use more. This is exacerbated by decreasing costs. Not only were the lumens per watt increasing, but the lumens per dollar were increasing as well. So this is the reason for continued exponential growth in artificial or anthropogenic light at night. It's not that we need it, but that we want it. Places that were too remote or too expensive to light are now being lit. More people leave their low-energy CFL lamps and LED lights on than they used to when they're using incandescent lights. Next slide. Looking around, we can see there have been improvements that began to curtail the waste of light. The optics were improved with lamps more recessed into the enclosure. Internal mirrors replaced scattering optics, and this significantly reduced the glare and light trespass. In the 1990s, Cobras went on a diet and slimmed down to flat belly luminaires with full cutoff shielding. There was no uplight, and glare within 10 degrees of the horizon was less than 10% of the total emission. This dramatically reduced light trespass and ultimately sky glow. It was so good that some citizens reported lights were faulty because they couldn't see the bright lamps. And with better control over the distribution of light, more light could be concentrated where it was needed on the roads. Then they replaced the older Cobra luminaires with new ones along Carling Avenue. The illumination of my backyard was immediately reduced by 30%. Next frame. Then the new technology leaped forward with LEDs. But instead of reducing light pollution from Carling Avenue, they increased the emitted light by 270%. So the promised energy savings were essentially evaporated. And my backyard is now twice as bright as it used to be. Yes, the light pollution didn't triple, but I'm still annoyed. What's so special about LEDs? And why are modern lights fueling this increase in light pollution? I guess we can skip a frame and then go to another frame. And one more. Let's look at the benefits of the older high-pressure sodium lamps. They were good for about 20,000 hours of use. Their color rendering index was not very good, but it gave what was promoted as less harsh light than the earlier mercury vapor lamps that they replaced. Since most of the light was emitted in the visual part of the spectrum that's dominated by our day vision, we could actually see much better with the high-pressure sodium than the mercury vapor light. Also, the high-pressure sodium lights look amber, and that results in a rather limited color rendering index, about 0.2. Now, the ideal is unity, and that's for the sun or even incandescent bulbs. And by going to metal halide lights, which emit more light across the visual part of the spectrum, you can get up to about 0.7, which is quite reasonable. The efficacy for these lights are now quite good, between 70 and 130 lumens per watt. Remember, this is about 10 times the efficacy of incandescent bulbs. Then, in the mid-2000s, high-intensity LEDs became commercially available. With the rising concern about light pollution, they were touted as the solution. But this was not to be. The reasons are hidden in the caveats behind what we commonly call common sense. Next slide. These LEDs are very different from heritage incandescent and high-pressure sodium lamps. They're not thermal sources of light. They're not emission line sources either. We're all used to the advances in solid-state electronics. They were the miracle that enabled computers. A common electronic component is a diode. It lets current flow only in one direction, but also has a curious side effect, which couldn't be seen unless viewed in darkness. The middle of the diode glowed as the component radiated the energy released when electrons on one side combined with the positively charged semiconductor holes on the other. They were further developed in the 1990s, which eventually led to Nobel Prize in 2014 in physics. An achievement for sure, but the light the LEDs emitted was terrible. For efficient conversion of electricity to light, the emission had to be within the blue part of the spectrum. Next slide. The next advance was in converting this blue light to longer wavelengths by placing a yttrium, aluminum, garnet, phosphor over the blue LEDs to absorb and convert this blue light from a band between 450 to 475 nanometers to longer wavelength band between 500 and 700, centered at about 600 nanometers. By combining this longer wavelength amber light with the original blue, produces what appears as white light. Varying how much blue light is converted changes the appearance from blue-white to warm white. Converting all the blue light results in an amber color that looks very similar to the light emitted by old high-pressure sodium lamps. Next slide. Why do LED lamps appear so darn bright? The lamp has to illuminate a surface, which is typically much larger than the area of the lamp itself. Taking a streetlight as an example, say about 8 meters high, the combined area of the lamp may be about 400 square centimeters. But the road surface may be the size of 2 times 5, it's 2 times by 5 times the mounting height, or about 640 square meters. So the lamp has to be 16,000 times brighter than the road. But wait, the reflectivity of the asphalt road surface is less than 5%. So the lamp has to be 300,000 times brighter than the road. And the blue light looks about 5 to 10 times brighter than the amber light. This is due to the structure of our retina and how blue light is treated by our brain. These are why the lamps look so bright, and the road surface is competing for visibility against the glare from the lamp. Now the solution, you would think, is to reduce the glare, not to further increase the brightness of the lamp, but that's what they do. So we go to, I'm going to skip the other portions of this slide so you can go next frame, and there it's good. Let's put some of these light levels, by the way, the reason I'm skipping those is the calculations are based upon another idea I had and haven't changed it. Let's put some of these light levels into an astronomical context. If you can see the moon, you can see the moon has the brightest luminance or glare, yet it provides quite adequate illumination for pedestrian level activity. We can see our way around. Now, this is not by luck. Our eyesight evolved over millions of years to make this happen. We can see at night, but we can't read. Well, reading is a relatively new technology, a new challenge, needing the paper to emit about 1 candela per square meter. And you can see that's about the luminance of Venus. And that corresponds to an illumination of about 1 to 3 lux, depending on how old you are and how good your eyes are. Against, next slide or next frame. Against a street light, our natural light hasn't even got a chance. There are orders of magnitude greater than anything natural. So what's the verdict? Next slide. Let's compare all these, the tungsten or the incandescent light, the high intensity discharge lamp, and the LEDs. In this table, red is bad, green is good, and blue is, well, so-so. With this table, you can see that LEDs are the clear winner. Although the gains are not so great between high pressure sodium and LEDs, LEDs have the additional benefits beyond what high pressure sodium lamps can produce. They can be dimmed. But this goes with a caveat. This assumes the light is used rationally and with common sense, though as we all know, common sense is not so common. Next slide. Our old building codes and best practices prevent us from taking full advantage of the wonderful attributes of LEDs to reduce light pollution. The homocentric approach to our treatment of the environment means that ecology shall not be factored into the cost-benefit equation. And since LEDs are expected to last longer than older lights, companies must sell more to keep in business. So they must install more lights where previously there were none. And that's exactly what's happening. Next frame. Also, industry lighting guidelines state minimum levels of illumination, and this precludes dimming. So one of the greatest benefits of LEDs is essentially discouraged, the ability to dim them during low traffic periods. They have to be maintained at the same brightness, unless a city has gone to the trouble of changing their lighting policy to allow them to be dimmed. Okay, let's advance a number of frames here so we fill up this slide. So the last thing that's coming up will be some text on the bottom. That's great. Here's an example of the energy we can save. This is a typical traffic density pattern over a weekday, and of course in a non-COVID era. Now this one has to be from London, England, but that's about the right latitude for most of the major cities of Canada if you don't count Southern Ontario. Most of spring and autumn and all of summer have their traffic rush hours during daylight. Since historically all light is to be designed for rush hour periods, this means that for most of the twilight and throughout the night, the roads are overlit. Allowing dimming can save between 50 and 75% of the energy used for lights, which accounts for 15 to 40% of the municipal energy budget. And this is something that incandescent lamps can do, but they're woefully inefficient, but LEDs do extremely well. Okay, next frame. So we can save more money and we can protect the and we can protect the night by making use of our night vision with better shielding and non-white light. These are easy to do with LEDs. We've been complaining about light pollution for decades. If you wonder why the RAC hasn't stopped it yet, consider there are only 3 active members in the Light Pollution Abatement Committee, and there are 37 million people in Canada. Think about it and what you might be able to contribute. So I think you can see that the new LED luminaires will be the solution if we can get people to use them properly. So as I said in the beginning, light equals hope, but only if they're used with care. We've made great advances in technology. Now we need to do the same for our society. And the next slide. And thank you for listening, and I'm open for questions.
Okay, thank you very much, Rob. That was great. I have a question here from Mick Wilson. Could you please explain further why road surface illumination seems more desirable to civic authorities than illuminating markings and/or items on the road surface?
Because it's best practice. And also the people that are, when I talk to the city officials, they default to the consultants that they've hired that recommend the lighting. And it depends on the RFP or the statement of work or what they're asked for. If they're asked to say, how much light should we put on the road, then they'll say, well, with LEDs, you can put a lot more. You can put this much down. For example, almost 2.7 times the amount of light that used to be on Carling Avenue in Ottawa. And the city officials can then quote that saying, we've been told by experts, and that's what goes, and that's what's being made. Why do they do it? Why don't the engineers think a little bit, carve into a bit more detail? They have been told, or they've been told that it's very complicated. And really, when it comes down to it, it's not complicated at all. It's common sense. And you can talk to a lot of people in the city, and they say, it doesn't make sense to me, but I guess they know what they're doing. And the answer is no, they don't know what they're doing. And so this is an era we're going through. In the past, when people thought that you're limited in how much light you can put down because the technology wouldn't allow it. Now the technology allows it, so let's put down more. There's another aspect to it, and that is light, and that is the sense of safety, the perceived safety you get when you're in light. It's only perceived, it doesn't give you safety. In fact, it puts pedestrians on display, and it also creates dark shadows off the road where you literally can't see what's going on. And yet, this is, it just seems to be buried into the lighting policy. The lighting policies are always inching up because, again, consultants suggest that you can do it. You can add more light here, you can add more light there. But once you add a light, you don't remove the lights aren't removed. This happens in national parks and provincial parks, where parks might be around for 40 years. Every year they put in a couple of lights or a few lights, and then when they do a lighting audit to be a dark sky preserve, they're surprised they have 500 lights scattered throughout their park. Now, why don't they just paint? Why don't they use paint? And the reason for that is that that's a different, the traffic department is used to dealing with light. They're not dealing that much with the furniture, the stuff on the side of the road. And also, when you put in the light, it's going to be there for 20 years. If you're going to paint the apron of the road or a line along the edge of the road, you got to do that the next year and the next year and the next year. That's an ongoing cost, and that's considered to be too expensive. Now, when you get into a park, it's very expensive to run the electricity lines through the park, and if there's a problem, it becomes a health hazard. So what we try to do through our Dark Sky Preserve program is suggesting that they literally paint the wood on the riser on the steps, the railings, for example. Instead of painting them nice dark brown that you can't see, paint a line of white on them so that even starlight will illuminate them. But why they don't do it the easy way, it's just that's not the way it's done. That's not the best practice. And that's something that has to change.
Okay, thanks, Rob. I got two more questions, just some quick answers here, and because we have to move on to observations. Question from Dennis O'Farrell: is this a problem of engineering schools?
Is it a problem of? Yes, it is. In some respects, you figure students, they're going to learn the latest. Well, if you look at who's teaching them, they got gray hair. So the gray-haired people, they learn from the back in the 60s and 70s. When light was not a problem. It was considered light is good, more light must be better, and that's what they teach. However, things are changing because now it's not a matter of the dark sky, but it's the ecology. People nowadays, students that's graduating now, are much more sensitive to the ecosystem and the balanced ecosystem. And by making it much, the RAC is trying to promote that as a benefit of reducing light pollution. It's not to see the sky, it's a matter of protecting the ecological balance. And once you light for wildlife, it's actually pretty good for humans, except for maybe near an observatory where you want absolutely no light. You can get by with a little bit of light without any problem whatsoever.
Okay. And Angela's asked, is there a petition we could sign or send to our friends across Canada to get people to look at this?
Well, there is, these petitions come up and evaporate pretty much, but the RAC has a light pollution abatement discussion group, and you can go on to the RAC's webpage under programs, you look under light pollution, click on that, and you'll see that there's a little link that takes you to a discussion page, and you can log and you can register for that, and then you can join the discussion, and people come up with things from all over Canada. There's over, I think, well over 150, maybe 200 people on the discussion group in the RAC. So it's very popular, and you get all this information, and they'll give you URLs to sign this petition or approach here. They can ask questions, and you can give your perspective on things. And if you want to be passive, you just read what people are posting, and you end up becoming quite experienced and quite knowledgeable in the topic after a while.
Okay, and last question here from Pierre Martin: are all of Ottawa's new LED streetlights dimmable? If so, do you know if there are any plans to better control their intensity at different times of the night?
That's a really great question, because some cities are doing that. They're actually buying dimmable lights. Now, the problem with dimmable lights is you need to have a controller inside. And that controller, I'm getting dated here, but I think about 4 or 5 years ago, was a $100 option. And when you look at how much energy LEDs are going to use over the lifetime, it wouldn't pay for itself. So some municipalities literally did not get the dimming option because it just wasn't worthwhile. Now, there's no reason for that. It's a $1.07 chip to put inside that, but you got to put it in. And but now in the past, it was an option that you had to pay through your nose for, but now companies are coming out with these as relatively low price options. It's interesting that since we've been promoting amber LEDs, more and more companies are now starting to produce LED lighting as an option, and some of their options also include dimming. It's interesting that some companies, they'll only dim about 20 to 30%, whereas there's one company in Ottawa that shall remain nameless. It dims 100%. You can dim it to whatever level you want. So in Ottawa, some of them were. They were failing because really the early adopter, they suffer with the failures. And I think they're getting better. Well, I know they're getting better ones now, given the companies that are giving it. Are they buying that dimming option? Well, they probably are. However, there's another caveat here, and that is the move afoot is the Internet of Things. And so what they want to do is they want to have all these controllers to be internet compatible so that they control all the lights in the city from a central location. And this really turns a $1.07 chip into a multi-million-dollar program, and the city can't afford it. So it'll be probably rolled out slowly, but unfortunately, it's beyond. It's getting beyond reason. It's a very simple thing to do, but then people say, "Oh, and we can do this, we can do this, we can do this," and the statement of work essentially escalates. And will the city of Ottawa start dimming? They definitely will, but it might take 10 or 20 years. And by that time, you can do your math with 2% or total of 4% growth every year. You can do the math at what's that? 4. So that's in the order of 8 years or so. So it's 4 into 72. That's a doubling period the city's going to get much brighter before it's going to get dimmer.
Right. Okay. Well, thank you very much, Rob. I appreciate that. Andrew, I see you have another question here, but we've got to move on at this point. And maybe you could flip an email to Robert on that question there. The Ottawa Centre, for those of you who have not visited us before, we have the M&M Moon and Messier Challenge over the break. So we can go to the next slide. Okay, so we have two images here. We've got Messier, sorry, it's the Messier Moon Challenge. I got to change my M&Ms around. So we're going to take a 5-minute break. It's currently 8:40. We'll reconvene at 8:45. And I'm going to mute myself. And you can take a bio break, grab yourself a coffee or tea, and we'll see you in 5 minutes. And the answers will be there. Okay, folks, we're going to get things back underway. So, Chris, if you can move to the next slide and get the answers. There we go. So the Messier was Messier 17, and the moonshot was that of Alps, which is one of the rails on the moon.
I'm going to present on my last year of aurora chasing. I'm a relatively new member. I joined the Ottawa Centre in June after attending a few public stargazing events. This year I had some time off from work and decided to invest it in traveling and pursuing photography of the aurora. And I'm going to share a little bit of what I've learned. Not all of it is probably accurate or right, but that can often be said about aurora physics and photography in general, which I'll get into a bit. First, I'd like to thank Dave and Chris and Jenna from RASC National for working so hard to get this working as a remote meeting. I know they put in a lot of hours, and there was a lot of technique and details that went into making this seem to run so smoothly. So thank you all, and I hope I can present some good content that stands up to our first remote meeting. This is me. You might see me on the video right now. If I'm going to turn it off in a minute just to minimize bandwidth. On the left, I'm in Yellowknife early last year. I have a big grin on my face because that's a relatively large aurora event behind me, and I'm just setting up the remote camera to snap at least one picture of myself. About a year later, I was able to collect enough photos from exploring and chasing the aurora to be able to put together some prints and some cards and sell them at local craft show here in Ottawa. And I made $80 and it cost me $100 to print it all. It's not going to make you rich or anything, but it was really nice to be sitting behind all these photos, and people would come and relate their stories about the aurora that they've seen or that they wish they could see in their dream trips. So I got to really connect with a lot of people in Ottawa by providing these prints. So what goes in between sort of hunting for the aurora and ending up with something nice you can hang on your wall? First, let's talk about why the aurora. You can see in the top right some stamps from Canada Post celebrating some astronomical events here. One on the right is Alan Dyer's photo of the aurora. That was quite a beautiful photo, and they had a photo op with him presenting it. The Canadian Mint loves to do glow-in-the-dark aurora coins. You can see just one there, a wolf howling at the aurora. They've got about 5 more, including one that celebrates citizen scientists who discovered a particular type of aurora. They were based out of RASC Calgary Centre. And the Alberta Aurora Chasers, which is also closely associated with RASC Centre, on Facebook is one of many aurora dedicated groups. It has 26,000 members, people who've all over the world. Some of them never heard of Calgary or know where it is, but nonetheless, they connect through the aurora and the photos people share and the updates about chasing them. What we're going to talk about is in 8 sections. A little bit of history, a little bit about where the aurora come from, starting with the sun, of course, how that sun energy gets to us via the solar wind and how it manifests as aurora. It's important to know these things. If you're going to be chasing them, you have to be able to predict them. And a bit of this talk is going to be about what I learned about solar weather and how the Earth responds to it, to know when to set up the cameras, to know when to get out of the car in -30 weather and start up the time-lapse photography. We'll also talk about where that light came from. Aurora, after all, is an emission in the Earth's ionosphere, and it is a spectral emission, has special lines. There was a lot of debate about where those lines came from, actually. And we'll try and build an aurora curtain together, color by color, emission by emission, to really understand what's going on. Talk a little bit about what forecasting really looks like day to day, week to week, what photographic equipment. It's not complex, but using it can be a bit tricky. And then we'll finally just take a look at 3 stops in my trip diary from this past season. We'll also touch a little bit on what do you do with all those thousands of photos you get. I'm sure that's an ongoing problem, is that you have terabytes of imagery that you wonder, what can I do with all this stuff? And the same applies with Aurora, even more so, because you're not taking super long exposures. What do you do with 3,000 photos a night? Let's start with aurora chasing in history from a photographer's perspective. You'll see some links at the bottom that are all called great reads that I put down there. I'll share those out later after the presentation, but they're all links that really inspired me. The first one is talking about the very first photographers of the heavens, the very first astronomers. It's a really good book, and you can get the whole thing for free on Google Books there. The first published photo of the aurora came almost as soon as they were able to get a camera up into the frozen north. Martin Brandel in 1892 wasn't the first to photograph him, but he was the first to publish it. And that was on a 9x12 plate on a medium format type of camera that he specially pre-sensitized to get maybe ISO 400 or ISO 800, which is very high at the time, especially from an f3.5 lens. So he published this first aurora curtain photo. And it took 60 years before the next sort of breakthrough in aurora photography, which was from J.R. Eierman, who's a really interesting photographer, physicist, engineer, jack of all trades, who really pushed his equipment and techniques to get photos nobody else could. He published in Time a photo series photographed in northern Canada, a series done on medium format using his own color film that was sensitized by pre-exposing it in the dark room, and that was allowed him to get very high ISOs and get these color photos. And you can find that whole entire, sorry, it's not Time magazine, it's Life magazine. You can find that whole presentation online, and it's just fascinating photos because it's also a real piece of history. You can see him holding a flashlight in his mouth, like we've all done, trying to clean up the foggy lens of his medium format camera. I would love to be able to send them a modern CMOS camera that we have now. Maybe they'd be angry, maybe they'd be amazed. Here's some photos I took in those 3 stops we'll go over later from the Yukon, Iceland, and Yellowknife. These CMOS sensors now are, the noise is almost at the quantum efficiency limit, and that really enables some amazing photography for Aurora. And we'll discuss later what the constraints and scope of that is. Hopefully you can see this video playing. Let me know if you can't. This is video that I took in Yellowknife. I pulled the camera right off the tripod because I was taking a time-lapse sequence and just turned it to video mode, ISO 28,000 and 24 frames per second, just to show you and to catch what the motion of the aurora is like during a minor substorm up in Yellowknife. And this is something that photos don't necessarily catch, is that it is a fluid motion. It is fast. It can be much faster than this. And it encompasses the entire sky, visible for thousands of kilometers. You can see as I pan down to the horizon, you can see it yellowing a little bit from atmospheric dispersion, same as, or atmospheric scattering, the same as the red sunset. And we'll go over these colors a little bit. Some of the motions here, the fact that the aurora split into curtains, that's not fully understood. Aurora physics is still very much an open problem with a lot of fundamental questions to be answered. The questions probably start with the sun, and we'll start with the sun about aurora prediction, where it comes from, and understanding the sun. The great read I have here is from one of the giants of aurora research, Dr. Aka Sofu. He wrote a synopsis of space physics research in the early days when he started, even before the International Geophysical Year. And this quick synopsis is available on the AGU pubs that are free right now, possibly because of the virus. But they've made this free and available. It's a great 10-page read. He bumped shoulders with all the giants and has an amazing career of discovering things that other people maybe took for granted or that just weren't apparent. Those of you who do solar work probably know about the 11-year season or cycle of the sun. You can see 3 of those cycles right here in this little graph. The difference is quiet or not quiet, and we're at a very quiet spot right now that I've circled in the bottom right. We're in a solar minimum, and what that really means is the sun is really quiet. That picture in the background from NASA shows a very active sun with lots of solar flares, with a dark coronal hole up in the north there. A lot is going on, but right now the sun does not look like that at all. Basically, is very quiet. A quiet sun has a very normal, continuous solar wind of particles of plasma emitted towards us. It's not necessarily amenable to auroral activity. What we're really looking for is features on the sun, even during quiet periods, and especially this last year. Aurora chasers were chasing coronal holes. This is really where all of our forecasting and all of our trip planning started. A coronal hole is kind of a cooler spot on the sun's surface. It can face us because the sun rotates in roughly 28-day period. And where it is dark, there's open field lines. The sun's magnetic field doesn't necessarily loop back into itself. It extends into the interplanetary magnetic field. And along that can travel accelerated solar wind. And we like that accelerated solar wind because it means there's going to be more energy pumped into the interplanetary magnetic field and ultimately into Earth's magnetic field, which generate the aurora. The good thing about a coronal hole, as opposed to say a coronal mass ejection or something that's more intense but short-lived and unpredictable, is we know a coronal hole is going to come around again in 28 days. So you can make your travel plans around it, and it'll give more consistent aurora for photography. You can see a post here from Richard Dunstan. He's at the Global Aurora Chasers Facebook group. He often posts these saying, hey, we've got a coronal hole that's maybe facing our way. That means we've got maybe 3 or 4 days until accelerated solar wind reaches Earth, and that gives us a chance of increased aurora spotting. You can see a hand-drawn solar synoptic survey on the left. The weather forecasters at NOAA or the Space Weather Prediction Center, still hand draw these maps of coronal holes, flares, sunspots, mark their polarity, and so on. It's an old tradition, and you can actually trace these solar synoptic hand-drawn surveys back many, many years. Here's a simulation put together by the Space Weather Prediction Center. It's a sort of a top view of the sun rotating. It's like a sprinkler. You can see in the bottom left, there's that orange area that's approaching. Sorry, I'll just start this video again. That's approaching Earth, which is this green dot right here. It's getting sprayed by higher velocity solar wind that's coming around from a coronal hole. And that's really what you're looking for. This particular model is okay. It's not a great model for prediction. You wouldn't want to buy your plane tickets based on it because it's a bit optimistic, but it's something we look for to know when the solar wind is going to reach Earth. You can also see the solar wind accelerating in one of those graphs from 400 kilometers per second up to 600 kilometers per second when that high-speed solar wind reaches us. So we know we've got some features in the sun that get to us at a higher speed, but how do they correlate with aurora? It's not simple. It's not common sense, I guess you could say. It doesn't just mean that this wind impacts the Earth's ionosphere and knocks and energizes ions. And again, we'll point to Aka Sofu, who talked about space physics in the earliest days, who talked about how it went from something that people pretty much had a good guess about to it actually being non-intuitive and a much more complex process. And the process we want to talk about is the Auroral Substorm. This applies to aurora photographers because it occurs on an hourly scale. And hopefully you can see this looping video from NASA. And what it's showing is magnetotail reconnection causing energy heading into the north and south auroral ovals. Solar wind is emanating from the sun. That solar wind couples with the Earth's magnetic field if the polarity is right. And that interaction compresses the magnetotail of Earth's magnetic field. When it rejoins or reconnects, it dumps a whole bunch of plasma particles and electrons into that north and south aurora ovals. So it's not just directly hitting us. You'll see the energy is actually folding over, reconnecting, and then falling back to the night side of Earth, which is really fortunate because it's on the night side that we want to photograph the aurora. There are day side aurora, but they're rarely photographed. It's a subspecialty. This is still very much an open problem. Magnetotail reconnection is still debated. There's satellites and evidence and data that even a paper published just last month discussed near Earth reconnection at the distance of geosynchronous satellites. So open problem, lots of debate yet, and the exact mechanism is not as clear as these NASA animations show. But suffice to say, the Earth charges up and then discharges, the magnetic sphere discharges into the ionosphere. And you saw those two donuts around the north and south geomagnetic poles. And that's really where you're hunting aurora. Those donuts go right over Iceland, Norway, the Yukon, Yellowknife, which is why those are aurora hunting hotspots, or cold spots, I guess, cold spots, especially in Yellowknife. On the left, we see a simulation of relatively quiet aurora oval. This forecast is out, I think, several hours. And on the right, we can see when it's very active. There's a big red area saying a lot of energy, I think 118 gigawatts just in the northern hemisphere. Those are the kind of aurora you'd have a good chance of seeing even in Ottawa. That substorm that we discussed, they happen many times a night potentially, and that's what an aurora photographer looks for. And this is what one looks like when it actually happens. This is the Aurora Max all sky camera up in Yellowknife, and I've lined up their time-lapse video with the magneto. I'm not gonna be able to pronounce the name exactly right, but this is the magnetic data from the Yellowknife Observatory, and you can see the magnetic deflection south. Here it comes as that purple bar moves towards it. There's a direct connection between the magnetotail reconnection and this main phase here of aurora activity, where you'd have your camera going really well, and then the aurora start to settle down again. This is a pattern you'll see again and again. You'll see a charge up and a discharge. And as a photographer, it tells you when you should go into your car and warm up and when you should be coming out getting your cameras ready, because it is at least somewhat predictable and you can start to sense these patterns. A good way to look at an entire nights of aurora is not to just look at video of it, because you'll be sitting there for a long time. Aurora all sky cameras are typically re-encoded into kilograms, which is sort of like a Richter reading or a seismometer reading or a heartbeat of the entire night's aurora. They take the central column of pixels from an all sky camera and stack them from left to right like spines of a book. And that'll give you a good idea of where the auroral curtains were at any time of the night. So you can see that sort of demonstrated here, a slice through the middle of an all sky camera. And then that corresponds to a spot at say 10 p.m. here. And this will tell you if the main features of the aurora are all over the sky, to the south of you, to the north of you, or kind of breaking up and dim. And using that, you can start to spot the substorms. Here's a night that I chose randomly. I generated these kilograms using Python and some data visualization software, OpenCV, where you can actually spot 4 substorms during one night. What they look like is the aurora curtains move south, which is towards the bottom of the kilogram, and suddenly snap north again when that magnetotail reconnection happens and fill the whole night sky with aurora. So you see the first one there is not too distinct. The second one is more distinct. You can see that swing down, fills the sky, and then dissipates. The next substorm is almost like a series of substorms overlapping. You can see 5 distinct peaks. And then much later in the evening towards the early morning, you can see one more substorm where the aurora snap back from the south and fill the sky and dissipate. The takeaway here is that if you see one aurora storm at night that lasts 20 minutes, don't go to bed, don't say what a great night, because there could be 2, 3, 4, 5 more of those happening from a coronal hole. One of the things that really makes the aurora magical, at least to me, is the spectrum, the palette of colors that you get, especially with a camera that can see, as you know, so much more than the human eye. Aurora mainly green because that's the strongest emission line. The electrons tend to flux in there at that 10 keV that interacts with atomic oxygen. Also, our eyes are really good at seeing green, but there's so much more going on. And I thought we would try and build an aurora curtain to really understand these spectral lines. And I'd recommend this read up at the top, The Green Line, a chapter in the history of aurora physics, in which we don't really know what the green line was until quite recently in history, like the 1920s. There's a shot also from the International Space Station showing the greens and reds. I don't know if somebody has mute on or not, but I can hear somebody on a keyboard right now. So please mute your mic if you don't have it muted. I'll just double check that. Here's a quick animation. And we'll start with the atomic oxygen. This is the green that you predominantly see if you see auroras. It occurs between 100 and 250 kilometers in the atmosphere, the ionosphere. And this is what you dominantly see because of the sensitivity of your eye, and also because that's the highest flux of photons coming out of the electrons that are pouring into the ionosphere. But there's more to it. I should mention that this atomic oxygen emission line was something that was not correlated with any specific transition that people understood up into the 1920s. And they assumed, like helium, that this is something, oh, well, new spectrum line, new element. And some people proposed calling this new element that was emitting this 557 nanometers or 5777 angstroms. They said, let's call it aurorium because we don't see it on Earth, but we see it up there. And it turns out it was just a transition line that they didn't see because they couldn't draw high enough vacuums in the lab. Something that aurora chasers really look for in reasonably active aurora is this pink to red fringe that moves very quickly along the very base of the aurora. It dances so much more quickly than the green, and that's because its transition is so quick. That only happens between 80 and 100 kilometers. And it's really vibrant. I think you saw some of it in the video there, some of that purple. This skims along the bottom of the curtain. It's so alive when you see it. And it's really what brings out the oohs and ahs in people who've traveled to see the aurora. That's from molecular nitrogen that's doing those emissions. In some photos, you'll often see kind of a purplish bluish extending above the green. And it also tints the green too, to make it less like a lime green and a paler green. This is the ionized molecular nitrogen that extends up to above 250 kilometers. Cameras pick this up and it's beautiful. The human eye doesn't necessarily, you see in some of the images we look at, you can pick up glimpses of it. Finally, oxygen reappears with a different set of emission lines from about 250 to 400 kilometers. This is that red that you see sometimes in Ottawa, say 2003 or so, 2001, when it's just on the horizon. This is the part that peaks over the horizon during very active nights that we see further south. And that was a harbinger of war in Europe in the Middle Ages whenever they saw the blood red over the horizon. These transitions all happen because there's different quench rates, different interactions. It's beyond the scope of this presentation. It's very complex. It's a very simplified view of it as I understand it as an aurora chaser, but I've managed to use this sort of model to understand just about every photograph I've seen of the aurora. Let's talk about forecasting for aurora chasers. Unfortunately, Newton doesn't help us like it does with planets, or like the Newtonian physics does with planets. We have to think about magnetohydrodynamics, the sun, and so on. And a great read here is all about NOAA's breakdown of the intense space storm that happened on Halloween 2003. This is their sort of after-action report about how it affected space weather, how it affected the grid, how it affected communications, GPS at that time. And it really shows that, yeah, aurora are nice to look at and photograph, but space weather is a very serious thing to predict. And we'll talk about that tidal pants on in just a second. Like all things worth measuring, somebody had to apply an arbitrary scale to it. And much like the Richter scale, the aurora have a scale where we measure the geomagnetic unsettled amount of energy around the Earth. It goes from KP0 all the way up to KP9. Think of that as like a F0 tornado or a small earthquake all the way up to a major earthquake. It's a semi-logarithmic scale. It's usually reported in 3-hour periods. You might get 4 reports a night saying it's going from up to KP3 down from KP0 during a night. And it's an aggregate of many magnetometers. It's not just one number. It's something that even is calculated after the fact and recorded historically as the definitive KP number, but it's also recorded 3 days ahead, or predicted 3 days ahead for aurora chasers. And it's a reasonably good way of saying, yeah, I'm gonna see the aurora and they're gonna be crazy, or no, I'm too far south in geomagnetic latitude to see them. Let's take a look at a really quiet night because we're in a solar minimum. This is just from March 25th, a few days ago, and you can see the 3-hour window of the KP forecast of between KP0 and KP2 on the left. You're not gonna see anything down in Ottawa. But if you're up in Yellowknife, you'd probably see some gentle green formations, maybe a few moments of active aurora. Now, there's a longer term forecast that stretches over 28 days. This goes back to the idea that, hey, the sun comes around every 28 days with the same features, and therefore we have a pretty good chance of getting the same solar wind, or reasonably the same solar wind 28 days later. And from that, you can maybe predict say the same solar or same coronal hole is going to come around 10 days or 28 days later, and it's a good time to go and grab your plane tickets and head to Yellowknife. Even though we're in a solar minimum now, there was a time in 2017 where I could stand off my balcony, which actually is looking right over the Aviation Museum here in New Edinburgh. And you can see early morning aurora breakup. This is during a KP7. KP5 or 6 is just visible on the northern horizon in Ottawa. But this was a KP7, and it was a lot more to see. You could almost see it with the naked eye, and this time lapse captures what I saw just from my balcony with all the light pollution of downtown Ottawa. It was still there. And we'll be coming around to these sort of conditions again in the near future, hopefully when we're no longer at solar minimum. In terms of just 1 hour notice of should I get my pants on and go outside, that's where pants on, pants off comes. We have the Discover and ACE satellites, which sit at the L1 Lagrange points between the sun and Earth. It gives us about an hour's warning for incoming pulses of solar wind, and especially these graphs here. I won't get into them in detail. These slides will be made available after the presentation, but suffice to say you're looking for a checklist of 4 things. A decent solar wind speed, a high interplanetary magnetic field, a reasonably high solar wind density, although the wind speed matters more because of the old energy 1/2 mv squared, so therefore V matters more to energy. But especially what you're looking for is that red line on the bottom right. You want your interplanetary magnetic field heading towards Earth to be negative. And that means just like two magnets that are opposed, when you bring them close to each other, they couple strongly. And if that interplanetary magnetic field component coming towards Earth in the next hour is the opposite of Earth's magnetic field, there will be strong coupling and therefore lots of energy transfer. If it's above there, the other three numbers don't really matter because there's not going to be coupling. All the Earth's shields are going to be up from Star Trek parlance. You're not going to be able to get any of that coupling. And so it doesn't matter what's happening in the interplanetary magnetic field. So negative BZ, negative interplanetary magnetic field matters the most for us seeing aurora here. So I can't talk about aurora hunting without talking about Alan Dyer. His Amazing Sky blog is of course amazing. His book, the iBook, is well worth picking up and setting aside the gig of space on your iPad. He talks a lot about his aurora hunting, and my equipment is not in his league, but we do share some commonalities here, and I'll go over those. But please read his blog. It is the definitive blog of aurora hunting equipment. This is one of my photos from the Yukon, and I want to share some ideas about what aurora photography really means from the photographer's point of view. It is astrophotography in that you got to know the night sky. You have to know your north and south. You have to be able to know all those things we discussed about forecasting. And you got to know your camera inside and out in the dark. When you can't feel any buttons, you got mittens on, you've got, you're chilly and shaking. You just want to know your camera inside and out, like all astrophotography. It's also like landscape photography, though. We're not doing long focal lengths, we're doing wide angle lenses, and that means bringing in a lot of the earth, a lot of the foreground, and really be conscious of how you frame and place the aurora. Otherwise, they're just kind of like in abstract splashes across the night sky. You got to give them a place. Like in this case, they're reflecting in a pond, there's trees pointing into it. I don't know a lot about landscape photography, but I really try and give a place for my aurora to exist. And finally, it's a lot like wildlife photography. It happens so fast and it can flare up out of nowhere and you can miss it. So you got to sit for hours and be ready to move fast after hours of waiting, maybe like birders and others can be familiar with. It's hurry up and wait, be conscious, and it might not be predictable and move the way you want. Maybe like sports photography too in that way. You have to be fast. How fast? Here's a sequence in real time. Hopefully it plays okay for you. About 1 frame per second that I was taking over Kluane Lake in the Yukon. And this is how fast thousands of kilometers across of aurora were moving. You can see the spiral form so quickly. It's thousands of kilometers across, hundreds perhaps in the ionosphere. And you have to be adjusting over several stops of exposure. You have to have your camera pointed in the right spot because this could have just happened behind you. You're not sure. So you're really looking for noise reduction off because you can't have those dark frame subtractions happening automatically in the camera. You have to be really quick with changing your shutter speed and your ISO because you're going to be moving from 15-second exposures down to 1 second or less very quickly. And you can easily overexpose your favorite aurora photos just showing up as white splotches. So of course you're shooting in RAW the whole time, maybe JPEGs as well. So the brightness can change over many stops, and you got to be ready for that. What lens you have matters with aurora a lot too, because you can't just track the object. It moves, and you want the brightest lens you can point at them. Here's an example of what the difference is from a kit lens, which works fine for aurora if you're just getting into it or traveling or doing it on the side, all the way up to a nice f1.4. Framing matters too. Again, wide is better. I'm finding 14, 16 millimeters on full frame or 11 millimeters or so on APS-C. That way you can really get the feeling of the horizon and then the aurora curtain stretching right over the top of your head. You feel much more immersed. 24 millimeters is a bit too tight, although a lot of great lenses are f1.4 24 that people have, or f1.4 20 millimeters that people have in their kit for other purposes. I went all out and went for 14 millimeter f1.8 Sigma, which is the widest and brightest I could reasonably get. And here's an example from that lens in a Sony a7 III. I'm usually a Canon shooter, but the Sonys just have the best sensors right now for this, although a lot of people still shoot Canon and Nikon. It's all great right now with full frame. This is going to be a bit of a jerky time sequence because we're presenting across the web here. But this is 4 seconds putting together a shot from the Ingram Trail in Yellowknife, and you can see how much motion there is. This is a relatively quiet night in Yellowknife, and still you get a lot of action, some great exposures. And all these were at 4 seconds at about ISO 1600. So again, the camera's a7 III, the Sigma 14 is really great, but also a ball head tripod. Because you're going to be swinging around and recomposing really quickly, and have a reliable intervalometer that you know how to use that's not going to freeze on you. Some of the secondary equipment that I like to have are hand warmers, not for me, but for the cameras, especially in Yellowknife at -30. You tape those hand warmers using hockey tape to the battery compartment all around the camera where it can get too cold. External battery packs to keep warm, and especially coffee. And just to mention, the most important photography gear, if you're going solo and driving around places like the Yukon or Iceland or Yellowknife area, which are all great for renting a car and driving around and exploring, is your rental car. Get a good one, get it far in advance, because it's your camera bag, your tour bus, your hotel room, it's your battery pack, your closet, and your kitchen when you're out all night. And especially it's your emergency shelter. Things can get really cold and dangerous really fast. And you can suddenly find you have no feeling in your fingers or toes and have to address that quickly. Your rental car is probably your most important part of photography equipment if you're not going to some resort to do photography up north. Let's talk about the trip diary just very briefly. This is the 3-stop trip diary. There were more stops. I went back to the same places more than once, but this is to give you an idea of what it's like in some of these locations. One of the first ones I went to last October was Iceland, and even on our way out, I knew there was a solar storm coming from the 28-day forecast. I booked my tickets, but it actually came a little bit early, and so during the flight I made sure, as always, to get a seat facing north on the window, and this was what we were greeted with for at least an hour over Labrador and Greenland. It was these amazing aurora that went right overhead of the aircraft. Interestingly, the people in the seats in front of us told us to be quiet because we're so amazed in taking these pictures. I guess they had their window closed because they wanted to get enough sleep to not be jet lagged when they reached Iceland for their aurora hunting adventure. And so we didn't bother telling them to open their window and see what they could see right there after they told us to be quiet. But yeah, an aircraft like this, it's a free aurora viewing, cloud free, and it can be a wondrous experience. When I got there, I was staying in the second largest city in West Iceland, Akranes. And the great part about Iceland is all coastline, tide pools, beautiful volcanic scenery, very stark, and lighthouses going back 100 years. And it makes for great foreground. You can see the aurora reflecting in the tide pools. You can rock hop all night, and you have the wondrous light of the aurora lighting things up, as well as the lighthouse as it rotates around. And it's warm. It's right on the coast, so it's only -2-3 degrees. You can stay out all night. I had a great time just spending time around the tide pool, trying to set up things and making sure my tripod didn't fall over or sink. What a great night. And this was during a particular coronal hole, which came around every 28 days during the entire fall and winter. And that's what I was using as the basis of my aurora travel, was chasing this one coronal hole every 28 days. And this is another shot of that old lighthouse, which they actually keep open and maintain. I met the lighthouse keeper there, said hi to him. I took his portrait with the aurora and his lighthouse and sent it to him as a gift. They do concerts in the old lighthouse right now because the acoustics are so amazing. Further down the coast, southwest of Reykjavik, just an hour or so, is Valahnukamal Park. And on this coast, there's sea stacks. And there's this amazing view out all night. People watch the sunset to sit behind this particular, or to set behind this particular sun stack or sea stack. You got to stay out later than everybody in aurora chasing, because the people on tour groups, their buses will pull up at 11 o'clock. They'll stay till midnight or 1 and then leave. And so the big knot of photographers will also leave at the same time. And then you have the whole place to yourself during the great time from 1 to 5 a.m. This was shot at around 4 a.m. local time, and it shows the breakup period of late night aurora, early morning aurora, where the curtains are now stabs of light that sort of function independently and can even pulse independently of one another. Of course, there's waterfalls everywhere in Iceland that people go to, and one of the most famous is Selfoss. It's extremely full during the day, but when I took this picture at about 1 a.m., the clouds were just rolling in, and I was the only person there. I used, I think, a 40mm lens for this to compress things a bit, and I got just a few frames before the clouds really came in. And of course, with waterfalls and mist, it gets all over your camera. You got to be wiping the lens constantly and hoping for the best. And that was a common thing being along the coast, is just you got to keep the salt water off your lens, and you got to keep that lens front element clean. But it was a nice long exposure with gentle aurora, and unlike most astronomical photography, clouds can actually do you a bit of a service, lend a kind of a 3D effect. I also went to Whitehorse, and from there you can drive along some amazing roads and some remarkable drives, including to Kluane National Park and Reserve. And on there, just as you enter the park, there's Kluane Lake, and it's a gigantic lake, and you can drive right across the south shore of it, where we spent a whole night on the beach with these large rocks, all alone, getting photos of the clouds and the aurora coming north of us over the lake. You couldn't go wrong with the compositions there. There was even somebody staying in an Airstream trailer that made a wonderful foreground for these lights. And this is the kind of photography you could get out over the lake, over the Kluane Range. Is probably my favorite photo from last year, because it really shows that sort of magneto-hydrodynamic effect of the aurora curtain when it gets energized, spiraling in on itself, almost like water circling a drain. And it also captures how it extends into the background and turns a bit more yellow because of atmospheric effects. There's also a lake south of Whitehorse that I went to, Marsh Lake, and it's a popular campsite, but there's a beaver pond that I found, and a pontoon bridge across the beaver pond. This is wonderful because no matter where you pointed the camera, there was ultra calm water, lovely sort of high tundra trees, and some great nights of photography. With some fairly gentle aurora. And of course, you had this nice bridge as a foreground. And again, this goes back to having some interesting foreground elements for the aurora here. You can see there's some yellow and some of that nitrogen purple as well. Looking straight up, you can actually have the aurora curtains right overhead, and that's called the corona. The aurora curtains are thousands of kilometers long, but only a few tens of kilometers wide. And when they're right overhead, you feel like you're kind of almost in warp speed or hyperspace, because the rays are coming down right at you from a central emission point at the zenith. And that's what we have here. You can also spot Andromeda in the top left. Canada is famous for the citizen scientists and photographers associated with RASC Calgary and the Alberta Aurora Chasers, for they found the Steve effect, and that is a new kind of aurora. I think it was 2016 it was first identified, and they collaborated with Eric Donovan at the University of Calgary and many other collaborators to identify this new auroral phenomena. And you can see it in this photo that I captured. They caught it from the south looking north. I caught it north looking south across the beaver pond. And the two elements of the Steve phenomena are the purplish white element that's separate usually from aurora, and this strange, very constant, unmoving green picket fence that's always associated with it, but caused by a slightly different effect. It's not fully understood, but even this year papers came out really defining a bit more about the Steve effect. And you can of course read up on that just about everywhere, but it's a great story. I even traveled to the RASC Calgary Centre for their definitive meeting and presentation on that, and what a fantastic bunch of people. They were associated with NASA on the paper that was published, and it was just to show that RASC and the photographers, citizen scientists, there's a connection there. There's still lots to be discovered and lots to collaborate on. Finally, you can't go aurora chasing in Canada without going to Yellowknife, and flying into Yellowknife, you'll quickly learn that there's the Ingram Trail driving out of town, over Great Slave Lake and to the east for about an hour's drive. And along there, there's many pullouts, many lakes, many opportunities for photography. One of my favorite photos last year I was up there for the Long John Jamboree as an ice carver. And we were staying at a hotel right by the Pizza Hut. And I brought my secondary APS-C camera. And I was just out heading back to the hotel. And I could tell even at sunset, you could see the aurora when the sky was still bright blue. There was going to be a great night. So I stayed out all night in a tiny forest of shrubs just behind the Pizza Hut, smelling pizza and photographing these aurora facing straight up. And that's actually light pollution lighting up the forest from the new hospital and its sodium lights right there. Nonetheless, the aurora were strong enough that that light pollution did not really figure into capturing the photos. And this is a time lapse I took just right before the quarantine as I came out of Yellowknife on Prelude Lake at the far end of the Ingram Trail. And this is just an aurora curtain looking straight north, relatively quiet, but still a lot of beautiful motion. And I just called this one a picnic for the eyes because even though there's lots of tour buses, nobody would get out of the tour bus and walk the few feet to these picnic tables sitting out on the ice covered with beautiful snow. And it's just a nice shot. Another place on Ingram Trail here earlier in October was the freezing lake with a bit of fog on it. And you can again see that mothership formation, the spiral of aurora on the horizon that looks so compelling. Talk a bit about processing and programming. After you've got all these photos, what do you do with them? From that most recent trip, I had relatively quiet aurora. I didn't get my timing quite right, and I showed up for the night in between two active nights. I got a relatively quiet night, but a quiet night is not a loss because the longer 20, 30-second exposures and the calm, unmoving aurora can allow you to take panoramics like this 360-degree pano taken out on the lake. And I decided that looks pretty compelling. You can see the curtains on the right, you can see the curtain overhead in the center, and then the breakup in the left. And you can actually wrap that in polar coordinates to get this entire aurora world around you that looks a little bit like the magnetosphere to me with the poles north and south. So playing with the imagery can be pretty compelling. Those kiograms I showed you earlier, I also decided to wrap those in polar coordinates. And it's almost like the face of a clock, but it also looks like the iris of a human eye. From sunset to sunrise, you can start to see these patterns. And I was pretty compelled to take these from the Aurora Max all-sky camera data and make a few of these sort of art pieces as a post-processing exercise. And you can even see on the one on the left and the bottom left, the clouds rolling in and the substorms. Finally, I am a web developer, and I decided to take that all-sky camera data and actually make an immersive interactive where you can visit any night of aurora from the all-sky camera and experience it firsthand. You can try this demo at the link below, and this uses, I think it has about 5 years of Aurora Max data in it for you to explore. And yeah, you can feel like you're there, and as well, you can quickly gauge using the kiograms what's going on through years of aurora. So I would encourage you to try it, and I'd love to know your feedback on this interactive demo using this open data. If you want to further explore this on your own, there's the spaceweatherlive.com website, the definitive dashboard, but also great reports and links of what's going on with the sun and the magnetosphere. 3 books I would recommend for reading, especially these days: The Northern Lights by Lucy Jago, Melanie Windridge's first-person experience. She's a plasma physicist and also a traveler, and it's a nice combination of both of those elements. And finally, by Dr. Aka Sofu, The Secrets of the Aurora Borealis, which is sort of a coffee table book out of print, but if you can find it, it's wonderful, covering the history and context of the Northern Lights. Every page, you can pick it up and read it randomly, any page, and you'll learn something new. I really enjoyed these 3 books, well worth a read. Of course, you have to check out Amazing Sky from Alan Dyer and his blog posts about equipment and his travels. He recently took an Aurora trip up the Norway coast on their cruise ships that are, one of which is dedicated for night photography, for astrophotography, and he was sort of the interpreter for the Northern Lights on that trip. Finally, you can follow me and my blog posts at Capture North on Twitter. That's my presentation here. I don't know if we have time for questions at all, but thank you.
I have a couple of questions here. Thank you very much, Jeremy. Those are just fascinating pictures. So in terms of questions here, somebody said they never heard of the Aurora chasers before, and how do you get started with them? Is that a Facebook group, Jeremy?
It is. The primary place to go for Aurora chasing is the several Aurora chasing groups. The Alberta Aurora Chasers, even though it sounds very local, is actually sort of the go-to place. The experts are there. There's a huge following. Richard Dunstan manages the global Aurora Chasers. Again, you just type this into the search of Facebook, it'll come up. And the Aurora Borealis Notification Group is the other one with about 25,000 members, and it's mostly Alaska oriented. But any three of those that you look up in Facebook, you'll be right in the thick of things almost immediately. So Alberta Aurora Chasers, Global Aurora Chasers, or Global Aurora Notification Group, I can't remember quite which, and then the Aurora Notifications Group. Find those on Facebook and you'll be right in the thick of it, and they've got tutorials, they've got links and FAQs.
Okay. Another question from Gordon was, when your first moving image was put up there, when was that shot? What time of the year?
The first moving image, yes, that was the first time I'd ever rented a Sigma f1.814 and an A7 III. That was in October of 2018.
Okay.
So that's just at the start of the season, approximately. The season kind of usually starts around September when you're starting to get 8 hours or 6 hours of good nighttime up in the Arctic.
Okay. And last question from Mike. What typical ISO settings do you use? Sorry.
Yeah, it depends on your camera, and it depends on your comfort level with the noise behavior of your particular camera. For the full frame cameras, I see people shooting anywhere from ISO 1600 at the low end to 6400 is a bit high. With a decently bright lens, an f1.8 lens, I try and keep it as low as possible. And that's usually 1600 or 3200, and I just leave it at that. And that also applies to the idea of ISO invariance in these modern sensors, meaning their noise floor doesn't vary with ISO as much as you think, and that's out of the scope of this talk. But read up on ISO invariance, and you'll find that it doesn't matter what ISO you set it to. You can always boost it in post later, and you'll get approximately the same noise performance. In the case of a Sony A7, it's from ISO 800 upwards is ISO invariance. Even if you've underexposed it in the shot, pushing the exposure in post will get you the same noise floor as if you shot at ISO 3200 in person.
Okay. I've got 3 more questions, and we're going to have to cut it off. Were you ever able to hear the Aurora?
I think so. People I talk to up north say yes. It's a debate. I was under power lines when I heard it, and my guess, because of being under thunderstorms and lightning during similar events, that it's some kind of inductive crackle from the power lines. But that was my experience. Some people have been nowhere near power lines and heard it though, so it's still a mystery, and it's open for fireside chat and debate.
Okay. Melody's asked, the photos look amazing. Are these images as seen through the camera, or is some photo editing used afterwards?
There's always photo editing done. However, it depends. During quieter nights, you got a 30-second exposure. You're not going to see very much in person, but as soon as that exposure is done, even the JPEG on your camera looks unreal. And the Aurora will flare up by 5-10 stops of brightness in a matter of seconds. And what you see in person is exactly what the camera captures and what you would just print off and frame. So it varies a lot, and you have to sort of adjust your technique for the type of Aurora that are happening that night. But there's times where I regret I almost wish the camera battery had died so I'd just look up and watch them move, because it's so much more captivating than sitting and adjusting your camera exposure.
Okay, and last question, do you recommend shooting dark frames with Auroras?
I don't think that's necessary. However, no, I'd say unlike other kinds of astrophotography, I've never had to do it. If you really want to get your background stars just right and do a really good foreground plate, I'll often do a time lapse of, say, 100 exposures of the Aurora, and then do one really good foreground plate with the focus shifted forward, and one really good background plate of the stars for reference. And but we're just sort of not in that realm where that's a primary consideration, I think. So I usually have it off all the time.
Okay, that's great. Thank you very much, Jeremy. That's an excellent presentation.
Hello. So most of most of my slides from the Winter Star Party, which is held every year in Florida Keys. Florida Keys, it's a chain of islands stretching from southwest from the southern tip of Florida across the Gulf of Mexico. Usually the party is held in February around the new moon for a week at Camp Wesam Key. Warm climate, lots of sun, quite dark skies make it a perfect break to have in the middle of the winter. Large body of water around the islands prevents big temperature fluctuations and therefore provides great seeing conditions. This is what this place is known for. Next slide, please. Astronomers from all around the world gather here to enjoy the favorable conditions for observations and astrophotography and see those rare perils of the southern skies that cannot be seen from the northern hemisphere, like Southern Cross constellation or Omega Centauri globular cluster. This year there were about 600 participants at the party. There is a high definition video on YouTube called 2020 WSP or Winter Star Party Recap. If you want to watch it, just Google the title in the YouTube. It's a great video with a fly through with a drone and the close-ups with people being interviewed, word about organizers, the participants, vendors, and so on. Next slide, please. One of my targets for this trip was Monkey Head Nebula in Orion. It's a hydrogen 2 region emission nebula associated with an open cluster, which you see in the middle. It's thought to be located about 6,400 light years away from Earth. Despite warm weather and favorable seeing, taking pictures of deep sky objects was a bit challenging this time, or this year rather, because of strong wind at the shore. And so I set up my telescope initially close to the ocean on the shore. The clouds would come in, well, it's inevitable, but the wind was strong and I had to move. So this picture was taken on the second night after I moved my scope inside the campground, and I took it with a modified Canon T2i camera and my 8-inch Meade Schmidt CAS with the guiding. But I got only about maybe 1 hour of exposure time total because of the clouds which would come and go, and especially periods of low transparency which would brighten up the stars. Next slide, please. One of the most popular and I would say coveted targets during the Winter Star Party is Omega Centauri. It's a huge open cluster in Centaurus. It's the largest globular cluster in our Milky Way. It has a diameter about 150 light years. It's estimated to contain approximately 10 million stars and a total mass equivalent to 4 million solar masses, making it the most massive globular cluster in the galaxy as well. Apparent dimension of this cluster is 36 arc minutes, and it's so bright that it can be easily seen by a naked eye. However, it doesn't rise too high even in Florida, about like 17 degrees or so. And in February, you would have to wait until 3 a.m. to see it that high. Cloud cover along the horizon, and in my case, tree line to the south, made its observation quite a challenge. So there was only a very short period of time, short window of opportunity for me to observe this jaw-dropping object and take a picture of it while it was not obscured by the clouds and in between the trees. So this is actually a single shot. I took it with exposure of 2 minutes at ISO 800. I wanted to take the second one, but there was already clouds coming, and then it hid behind the trees. So I'm happy that I saw and took a picture of it. It's right now on my list. Done. Next slide, please. Good seeing conditions in Florida, just begging you to take a look at the planets. shortly after the sunset, Venus was seen bright in the skies on the west, relatively high, 36 degrees, and relatively big, about 17 arc seconds. This is what it looked like in a visual light on the left. There are claims on the internet that you can see Venusian clouds through a deep violet filter number 47. I tried to use it for both observation and imaging, but didn't get much of a different picture. Image just wasn't contrast enough to distinguish any details through the cloud, so through the blanket of clouds. There's just like a hint of something slightly different at the bottom. I'm not sure if video would show it because of the compression, but if you look carefully, or maybe it was my imagination, there was a little something at the bottom, so it was questionable. Next slide, please. For comparison, cloud coverage becomes quite distinct when using a specialized Venus UV filter, which allows only a relatively narrow band of ultraviolet light, about 350 nanometer frequency, 60 nanometer bandwidth, to get through. The clouds of Venus absorb or reflect more light depending on their thickness, and this can be photographically captured with a camera. So the use of such a filter allows us to take a peek at the cloud structure. Apparently this it's an interference filter, and it's quite a piece of equipment created by Bader, the manufacturer. Their website tells some details about the challenges which they had to overcome in order to build this filter. But yeah, the result is proportional to your investments, so quite expensive filter, and you get more information, more details than that visual number 47. Next slide, please. But that wasn't the main raisin in the bread or main event for the star party, for me at least. The main event was the occultation of Mars with the moon. This was supposed to happen on February 18th, early morning, around 7:13 a.m., which would be at the end of the first night at the star party. I took this picture a few hours ahead of the event, around 4:30, still from the shore, because it was the first night, when Mars, which you can see as a bright dot below the crescent, was relatively far from the moon. Then I looked at the planet through the telescope and realized that I will not be able to take any good pictures or videos from there because the wind was too strong and the image of the planet was dancing around the field, of view. So I had to relocate my telescope away from the shore so that the trees around could protect it from shaking. It was done in a rush, and as a consequence, a few tiny dust of particles got carried by the wind and stuck to the planetary camera filter, something which I noticed only later. Next slide, please. So meanwhile, Mars was getting closer to the moon, which was nicely lit by the Earth shine. I hope you can see a little bit of both the crescent and the round shape of the moon with the Earth shine. But it was still quite windy, and although not as bad as at the shore. Although the sun was supposed to rise at 7 a.m., which would have been already quite bright, the observations, they were possible even during the daylight because of the contrast. So the bright planet and the bright moon were quite distinctively seen on the background. If you go to the next slide. So this was taken at 7:09 a.m., 4 minutes before the actual occultation. So what was supposed to happen is the planet would hide behind the lunar surface. And this is not the best image of moon that you can see because again, the planet was quite small and far, only about 5.2 arc seconds. I used a powerful Barlow lens, but also after the sunrise, the air started warming up, and the seeing deteriorated drastically. So the details of the lunar surface cannot be clearly seen in this picture, even though it was made as a result of about 1,000 frames of video stacked together. Next slide, please. So a few minutes later, about 7:13, Mars started to hide behind the lunar surface. This was the moment I waited for. Surprisingly, the planet movement looked much faster during this ingress because of the relative distance between Moon and the planet to each other. So processing this picture was a bit more of a challenge because I only had a very limited number of frames to stack. Also, while processing this video, I've noticed quite distinct artifacts created by those dust particles stuck to the camera. And I had to retake the flats and put some work to make it look more or less without those dust particles showing up in the image. If you go to the next slide. This is the actual video which I took at the 3 times speed, if you don't mind running it. As I mentioned, I did apply the flat frames to remove those artifacts, but also I tried to more or less stabilize the image because it was still windy and the image was shaking. The duration of this video, about like 8 to 10 seconds, it's actually 30 seconds of the real time, so it's 3 times speed. This was quite an amazing experience for me because I knew that this is going to happen, and I was preparing for it. And it looked actually exactly as it was kind of shown in Stellarium in the preview when you enter the date and location and see closely the occultation. This is exactly what Stellarium predicted that to be. Which is just to prove how precisely we can predict events like this, occultations or eclipses, and how little they affect our real life. Thank you.
Thank you, Taras. That was great. So next up, we have Jim Thompson. Give me a second here. Okay, you're unmuted, and let me just make you the focus. There you go, Jim.
Right. Everybody can hear me all right?
Yep.
Okay. So my observing report this month is the observing challenges that were given last meeting. First object is Palomar 4, which is a globular cluster located in Ursa Major. It's one of a series of globular clusters that were found during the photographic sky survey done in the 50s at Mount Palomar. That's how it got its name. Now this globular is quite dim. I know it's not really standing out. If we go to the next image, please, Chris. There, I've annotated now the image to show the globular cluster. I've also identified a couple of small distant galaxies that I happened to catch at the same time. So this globular is quite dim, as are most of the Palomar series of globular clusters, and that's because it's very, very far away. This particular globular is about 65,000 light years away, which is more than halfway across the diameter of our galaxy, so pretty far. This particular image was one of my first images captured using a Mellencam Extreme back in 2013. This is when I was first learning about video astronomy. It was taken through an 8-inch Schmidt-Cassegrain from my backyard in Ottawa, and it's a stack of 4 2-minute frames. Next image, please. So fast forward 3 years to March 2016. This is an image of M65, another observing target for this month. It's a spiral galaxy located in the constellation Leo. So it's actually a good time of year to observe it right now. It's well placed in the southeast at night. It's considered an intermediate spiral because it is midway between a proper spiral and a barred spiral. I don't know if I'm going to see if the annotate works here. There's sort of the remnants of a bar that kind of goes across that way. It's hard to see because of the angle that we're looking at the galaxy. Other features that are interesting on this galaxy is along the left edge, from our perspective, in this photo, is a large dusty lane or arm that kind of hides the galaxy spiral arm along this edge. And again, that's due to our perspective. The clouds of dust in the spiral arms are blocking our view of the rest of the galaxy behind it. So it's kind of an interesting features on this galaxy. It's relatively close at 35 million light years away. This was captured with a 10-inch Ritchie Chrétien from my backyard and a Lodestar X2 monochrome camera. And it's a stack of 10 30-second frames. My final image, or the next one, is of the Lunar Observing Challenge this month, and it's the crater Aristoteles, which is this guy right here. It's about 87 kilometers in diameter, and the large crater below, down here, is called Eudoxus, and it's about 67 kilometers in diameter. They're quite interesting craters to observe this particular phase of the moon. This is actually just before the last quarter phase, so I had to get up quite early in the evening or early in the morning to catch this particular phase. But it's interesting because it really shows the debris field around the crater, especially up in this area. Some other interesting objects to observe in this particular part of the moon, of course, is the Alpine Valley, which was our M&M challenge at the break. And another one of my favorite objects to observe is the crater Cassini, which to me looks like a sideways happy face. Always cheers me up to see that when I'm observing. So this particular image was taken with a 10-inch Ritchie Chrétien and a ASI 183 monochrome camera and an IR pass filter. So this is only infrared light we're looking at here. And it was a stack of the best 200 frames out of 3,000. And that's it. Thank you.
Thank you very much, Jim. Next person up is Richard Taylor.
Okay.
Yep, you're on. Sorry. Okay, go ahead.
Okay, so just after the last RASC meeting, I headed halfway around the world to the Philippines, hoping to have a lovely March holiday. And then everything broke loose on March 13th, and we had to hurry home again. But I did get one nice night out into the stars, and this gives us a perspective on the dippers that we don't normally see from Canada. This is looking north towards Manila. We were about 100 kilometers south of Manila, but most of the sky glow there is caused by a city on the other side of the channel called Batangas, where they have a huge oil refinery. So the big glare towards just the right of the middle is from a gas flare on the oil refinery. So anyway, this is just an unguided, untracked photograph with my DSLR and fairly wide field of view. But I noticed when I got back that there was a comet up in that area of the sky. So I zoomed right in on my photograph and looked very carefully at the star map. And could we see the next picture? There was one little dot up there that didn't correspond to any star on the star map. So I think I caught the comet Atlas that we heard about earlier this evening. So I was quite pleased to see that that had come through. But as I say, we only had one night out under the stars. Most of our time was there for diving. So next slide. These are the stars that I was looking at most of the day.
Okay, thank you very much, Richard. So next up is Bob Olson. So just give me a second while I set things up here.
Okay, how are you doing? This is just a sec here. I've got something on my screen. This is a picture of M63. It was taken not this week, but last week when I returned from Florida after 2 months away from my equipment. I took it on the March 24th and 27th over 2 nights. It is 11 hours of total exposure. It rises, it's high in the east at sundown, and it stays up all night, so I just stayed right on it. I was not very interested in switching targets because after being away for 2 months, every single one of my astronomical imaging programs wanted to update, and nothing operated after that. It took me 11 hours previous to this to get the image to go. 2 nights of imaging. In actual fact, the second night wasn't as good as the first night, so I'm not totally sure the extra 4 hours made much difference. Anyway, thank you very much.
Okay, thank you. So I've got John Thompson here. Hang on a second. Are you there, John?
Yes, I'm here.
Okay, you're getting quite a hum on your line there.
Okay, well, is my telephone, can you hear me properly?
I can hear you. Just speak loudly.
Okay, well, that's the best I can do.
Okay.
Yeah, unfortunately, that we did our rehearsal on Wednesday and my system worked, but I couldn't get anyways, technical problems today, so I've just connected my telephone. The first image, this was taken on February 14th of Mercury. It was in the twilight sky, and it was minus 20 degrees out there. That I was out for 25 minutes. And turned out my DSLR camera wouldn't work in those temperatures. I think the cold drained the batteries, but this was taken with the Ricoh 360-degree camera. I was able to get one shot that you could just see it there in the twilight. The greatest elongation, which is its angular separation from the sun, was actually the Monday the 10th, but there was not good weather, so this is my first opportunity to see it. And it was only visible for about 10 minutes, but then it's actually first magnitude, but you wouldn't know that because of the twilight sky. And after 10 minutes, it just faded into the horizon haze. So the next picture was taken 5 days later when I was down on the Florida Keys. I didn't know that Taras was down there. So I was at the Winter Star Party also. And these were taken, I think, the night after Taras's pictures, was the first night there. I was doing mainly visual observing. Now this was one of my first attempts at doing prime focus photography with a refractor, a telescope. It's a 120 millimeter f5 refractor, and it's not an Apple or anything like that. It's just a regular, at least it's not advertised as being especially color corrected, but it's actually not bad unless you push it to higher powers. Now the first image here, this is Messier 41, which is in the constellation of Canis Major. It's about 4 degrees south of the bright star Sirius, and it's a very good binocular object. If you get Sirius in the top of your binocular frame, you should be able to see this star cluster. And the way I've ordered these, I'm going from nearer to farther distances. Now this cluster is 2,300 light years away, and it's like a sort of a bright coarse cluster. Next cluster, or the next image, is Messier 46 in Puppis. Now that's in the Milky Way that runs to the east or left of Orion. And it's about twice as far away. It's 4,900 light years. And what's unique about this star cluster, I don't know if you can see it, but right down at the very bottom edge of it, you might see a little blue-green circle. That's a planetary nebula, which is planetary NGC 2438, and it's the only cluster that I'm aware of that's associated with a planetary nebula. Like Ross mentioned that there was a nebulous cluster, there was a cluster with the emission nebula, and there are also clusters with reflection nebulae, like the Pleiades, which reflect blue light, and parts of the Trifid Nebula also reflect blue light that the dust preferentially reflects blue. But this one is basically it's not quite a supernova remnant, but it's a star that's in the process of dying. It blows off its outer atmosphere, and they make what's known as a planetary nebula. So that's also a nice little cluster. Now the next one, the next two, are in the constellation, or this is M81 and M82 in the constellation of Ursa Major off the Big Dipper. Again, if you have a really dark night and good-sized binoculars, these are binocular objects. These are relatively bright as galaxies go. M81 is the brighter one to the top center, and if you look, you can just see a faint trace of spiral arms there. This image was 3 30-second exposures, which were stacked. You notice that the focus sort of varies across the frame. I was using a homemade adapter, which was a friction fit, and it seemed to have slipped a little bit. I have a better adapter now that should avoid that. But the other brighter galaxy is M82. Both of these are about 13 million light years away. It's an edge-on galaxy. And then off to the right of the frame, there's another faint galaxy, which is NGC 3077, and they're all part of the same group, which is about 13 million light years away. And these are, like I say, were all taken at the Winter Star Party. Now, the last image is another pair of galaxies. This is in the constellation of Leo, and I was having trouble also. It was, as Taras mentioned, it was very windy, and the clouds were sort of coming and going, so I had to shoot this between clouds before they get covered up again. So this is a pair of galaxies that are about 33 million light years away in the tail of Leo. The brighter one is M95, it's 33 million light years away, and then the dimmer one is M96, which is magnitude 9.7 and 31 million light years away. So this was just a single 30-second exposure because, again, because of the wind and the clouds, I wasn't able to get as many exposures as I would have liked. But anyways, that's a start, and I'll be doing some more experimenting with this setup in the future and hope to get some better images. So that's it for me.
Okay, thank you very much, John. And Paul Cleninger, you're up next.
Well, good evening, everyone. I hope you're all doing well out there in virtual meeting land. I've got a few items of interest for you this evening. For those of you who are fans of Star Trek, you might recognize this scene from The Next Generation that depicts the start of an epic battle between the Federation and the Borg. It occurred around the nearby star Wolf 359. What I have to you tonight is not nearly as epic, but hopefully ends on a more positive note since the Federation did lose that battle. What I have is actually a rather interesting observing challenge that some of you are undoubtedly already aware of. The challenge is to observe that star, Wolf 359, but with a unique twist. But first, a bit of background. Next slide, please, Chris. So Wolf 359 is the 8th closest star to us here on Earth after our sun, at a distance of just under 8 light years. It's a small red dwarf with less than 1/10 of the mass of the sun, and it's not much larger in diameter than the planet Jupiter. It's in the constellation Leo, and it's pretty dim, glowing feebly at magnitude 13.5. That alone makes visually observing it a bit of a challenge. Under a dark, moonless sky, you might be able to see it with a good 6-inch telescope, but an 8-inch or larger would be better. And if you're imaging it, it's an easy target with a 6-inch or even a 4-inch, provided you know exactly where to point it. So the unique part of this challenge is to observe that star on a specific date and time. Next slide, please, Chris. On April the 23rd, in 3 weeks basically, at precisely midnight, the New Horizons spacecraft, currently about 47 astronomical units from the Earth, will be commanded to have a look at that star, Wolf 359. And because Wolf 359 is very close to us as stars go, an image taken from 47 astronomical units away, compared to one taken from Earth at the same time, will reveal something quite remarkable. From the spacecraft's perspective, Wolf 359 will appear in a slightly different position in that image with respect to its neighboring but more distant stars than the same image taken at the same time from Earth. This is the result of parallax, and astronomers use this technique routinely to measure the distance to relatively nearby stars. They take a picture of the target star they're investigating at one point in time, and then 6 months later, they take another picture of it. In those intervening 6 months, the Earth has moved halfway around its orbit around the Sun, effectively shifting its relative position by 2 astronomical units. The unique thing about this opportunity is that with New Horizons, we'll be able to take 2 simultaneous images from 2 different vantage points, 47 astronomical units apart. This is going to yield a much larger parallax effect. Next slide, please. So in preparation for this event, I took a test image of Wolf 359 last week, indicated by the arrow. When the New Horizons takes its image in 3 weeks, Wolf 359's location will be roughly at the position indicated by the green circle. I'm hoping to image Wolf 359 again at exactly the same time. And once the New Horizons picture is made available, I should be able to use both images to create a stereo pair. If that works out properly, it'll allow me to see Wolf 359 in 3D with respect to the other more distant stars in the field. That's the theory anyway. At any rate, it'll be interesting just to even observe the difference between the 2 images. But even if you're not into imaging, if you're able to observe Wolf 359, why not try to make a careful, detailed sketch of its position with respect to the stars close to it? That's also why I suggest an 8-inch scope or greater. While you might be able to see Wolf with a 6-inch, you'll definitely need an 8-inch or larger to see the stars closer to it, since they are noticeably fainter. Then you can compare your own sketch to the New Horizons image and see the effect of parallax with respect to your own observations. Just a side note on this too, New Horizons will also be taking a picture of the closest star to us after our Sun, Proxima Centauri. This will allow southern observers and southern observatories to participate in this rather unique opportunity, and also give us a chance to determine the distance to our nearest stellar neighbor with unprecedented accuracy. So good luck with those observations. Hope we'll get clear skies. All right, next slide, Chris. So the next item I have for you is regards Comet Atlas, so that Dave mentioned. This comet was just discovered back in December, and last month I showed you this image taken on February the 24th, when it was about magnitude 12, but brightening fairly quickly. Next image, please. So I took this image just last week, and the comet's reached now a magnitude of about +8. Not quite yet naked eye visibility, but considerably brighter and easily visible in a small telescope under dark skies. And it's sprouted a tail. If some of the projected magnitudes for this comet come to pass, it'll soon reach naked eye visibility, and by mid-May, it could be as bright or even brighter than the planet Venus. At that point in time, it will be seen best in the low in the northwest sky around 10 p.m. in the evening. Let's cross our fingers and hope the sun doesn't tear it apart before then, which is also a possibility. Next slide, please. And speaking of Venus, for those of you that didn't get a chance to see it, these last two couple of slides I have for you were just taken this week, this one on Tuesday night when we had a nice clear sky. and you can see Venus approaching the Pleiades from below. It was nice and clear. Unfortunately, the next few days were not quite as giving, at least in my location. And but I took an image anyway last night. So the last slide I have for you is from last night. Here you can see Venus just under the Pleiades, and it was bright enough so that it would illuminated some of the thin clouds that had started to move into my area. But it yielded a kind of neat effect. Unfortunately, Venus is right in the Pleiades actually right now, but it's cloudy in Ottawa as usual. And of course, this RASC meeting prevailed. So that's why we're all here tonight. Anyway, stay safe and be well, everybody, until we virtually meet again next month. Cheers.
Thanks, Paul. So next up, we have Chris Tarrant.
Okay, thank you, Dave. As many of you know, I had some of my first experiences with some wide field astrophotography recently, and I wanted to try to keep up that skill. So I had a nice opportunity last weekend at our cottage to take this wide angle view with lots of different features in it. And it was done up at our cottage, which unfortunately I'm now prohibited from going to, since we're an Ontario resident in a Quebec cottage. But I'm known around the lake for doing a lot of public astronomy, and I'm always posting these kind of photos up there. And to the non-astronomers, I like to animate the image and show people what's there. And this is self-explanatory. You can see, Venus and the Pleiades and Taurus, Orion, and Canis Major. And I had the fun of adding the image to this of the light dome over Ottawa. And it was interesting, it caused a reaction from a few cottagers who said, "You've got to be joking. We're 120 kilometers as the crow flies from this lake to Ottawa. How could you possibly see the light dome that far away?" And I had to explain, well, it certainly is possible. The rule of thumb of light going out 3 to 5 times the diameter of a city. But just to prove it to myself and to prove it to other people, I took a good compass bearing on that light glow, and then went to the same kind of maps that Rob just showed to us to have light pollution. And I plotted the location of our cottage and the direction of that glow. And it didn't take any more convincing to people that 120 kilometers away, you can still see the light dome of Ottawa. And this image tells you that equally, I don't waste my time turning to the southeast, because you can imagine the glow that we get from the monster city of Montreal.
Thank you very much, Chris.
Since I've got the microphone, just an announcement here. We are coming up on International Astronomy Day on May the 2nd. It would be normal for the Ottawa Centre to have events indoors, outdoors, day and night at the Aviation Museum, just as our friends from the Ottawa Valley Astronomy Group will have their event at Chapters. It goes without saying, with COVID-19, it is unlikely that these will take place. But Dave, if you can open the mic to Jim, he's going to talk about an idea for the event.
Yeah, you're open, Jim.
Hey, thanks. So with the success that we're having using this Zoom platform for outreach and for astronomy, my children's scout troop is using it. It's being very successful. So we are thinking of trying to use this technology to have some sort of a virtual star party on May 2nd. So stay tuned for more information about that. Thank you.
Okay, thank you. So our observing challenges last month. I don't know why my video is not coming up, but anyways, we'll leave it there. We had the M65, intermediate challenge was NGC 2438. Advanced challenge was Palomar 4. Lunar challenge was Crater Aristoteles. Next slide. So our beginner challenge for this month is Messier 95. Next slide. Intermediate challenge is NGC 2905. All these will be in our Astronotes newsletter, so that's why I'm moving through them fairly quickly right now. We're getting on time-wise. Next one. Advanced challenge is AGC 1060. Okay, next slide. Our lunar challenge is crater Piccolomini. It's the first time I've seen the slide, sorry about the pronunciation there. Anyways, that's your lunar challenge. Next one. There's a summary of what our challenges are for this month. If you can get some pictures of them, that would be great. Next slide. Okay, the library is at the Aviation Museum, and guess what? It's closed. So there will not be a pick of the month until we can get back into the Aviation Museum. Here are the people that are involved with the Ottawa RASC, and they're great people to help us out there. Next slide. We had 125 people out this evening. That's amazing. And people from all over. We had somebody from Iqaluit, and we've had, hopefully we got some folks from Sudbury as well. Thank you for joining us. I think we've got a couple more slides. We normally have our post-meeting entertainment at Grace O'Malley's. That's not happening. Okay, next slide. Okay, membership-wise, if you're not a member of the Royal Astronomical Society, you're always welcome to come and join our meetings, either virtually or in person. But there are benefits of being a member. A regular membership is $86. A family membership is $80, plus $13 per adult and $7.10 per youth. And youth membership is $52. The benefits are, okay, we have our Ted Bean Loan Library. We have our regular book library. We also have the Fred Lawson Observatory out near Almont. Those are all benefits of being a member of the local RASC. Next slide. In addition, as a member of the national organization, you get Sky News, you get the Journal, and you get the Observer's Handbook every year. And Astronotes is our amazing local newsletter that's sent out every month by Gordon Webster. So thank you, folks, for that's the benefits of joining. What's our next slide? Our next meeting, there we go. I would strongly suspect, given where things are going, that our next meeting will be virtual, Zoom webinar, and we will be posting the information to Facebook and to our website, the links for signing up for that. And I'm still working on the talks for that, but I can tell you that Simon is coming back to give us some more details of Venus. I'm looking forward to that particular talk. That one has been confirmed for sure. So thank you very much, folks, for coming out tonight. We'd love to get your feedback. If there's things that we could do better, that would be great. This is our first attempt at this Zoom stuff, and hopefully it went fairly smoothly. Thank you very much. Have a great evening. Stay safe.
If I can chirp in one extra announcement, Dave.
Yep.
One of the beautiful advantages of a webinar format is this entire session has been recorded and will be automatically converted to a video with audio and a separate text file of all the chats that have been going on. And as soon as we can, we'll have it posted available for anyone to view.
Super. Okay, folks, thanks for coming out, and we'll see you all next month. Have a good evening. Bye now.